welcome to video on lesson 9.2, page 380 in our Big Ideas book where we're continuing data analysis and displays. Ladies and gentlemen, it is such a pleasure to be with you tonight. And we are going to apply what we learned to draw the line of fit for a scatter plot. I'm telling you, what we're going to be doing tonight involves 85% of stuff you've already done. So pay attention, pay attention. You listen, you take down the notes, you will learn this. And then we're going to analyze the equation of that line. So we're going to draw a line, and then, as we've done before, we're going to write the equation of that line. And it says, how can you use data to predict an event? That is our essential question. How can you use data to predict an event? And if you're like me, the notes from the top of page 3 were a little bit inadequate. So, ladies and gentlemen, I copied it right from the internet because I thought it was pretty good. And then in this case, though, I called the line of best fit. I'm going to cross out the line best, the word best, crossing that out because we're just doing lines of fit. When you go to algebra, you will do a line of best fit because you will be using a graphing calculator. You will plug in all the data in the appropriate way, hit the appropriate buttons, and it will give you the equation of the line that is the best fit for the data. Because that's what the computer can do for you. We are going to estimate. So we call it a line of fit because we're going to estimate that line. And then we're going to use what we know from that line to write an equation of the line. And of course, every time we write an equation of a line, we want to write it in slope-intercept form, y equals mx plus b. So a line of fit, sometimes called a trend line. It's a straight line that best represents the data on a scatter plot. We know what a scatter plot is. We know how to dot all the points and data on a scatter plot. And so what we want to do is we want to draw a line that best represents that data. So that line will be kind of like a median because we want it to kind of go through the middle of the data. What I mean by the middle is so that there's approximately the same number of data points on each side of the line, and each one of those data points is approximately the same distance, give or take, from that line. We'll talk about it when we get there. Anyway, and this line that we draw, there's opportunity that it might go through some of the points. It might not go through any of the points. It might go through all of the points. That would be a perfect situation if it went through all of them because that would make it super easy. And then after we've drawn this line, we can again write the equation of that line in slope-intercept form and use that to estimate and predict data on the graph. Ladies and gentlemen, let's just do it. So right here we have a table that shows the number Y of customers in a line at bank X minutes after noon. So here we go. We've got this graph, and I'm looking at the X values in minutes, the Y values as customers. Let's label our graph. So this is time in minutes on the X. And we're just going to go by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's good, probably good enough since the scale, or since the values only go from 1 to 7. We're probably gone far enough. And on the Y, the highest number is 15, the lowest number is 3. Let's go by 1 and see if it fits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, it goes all the way to 16. And of course, this is number of customers in line. All right, so now that we've labeled the axis and we have our scale on there, ladies and gentlemen, pause the video and go ahead and plot those points in there very quickly. And welcome back. If you did, then this is what your points might look like. Right there, if you graphed them at the same scale that I did. And so now, ladies and gentlemen, we made a scatter plot. What we want to do is we want to draw this line of fit. So here's what we're talking about. This is really the only thing that's new for you. The only thing that's new for you. Drawing that line that kind of goes through all of them. Because you can see, and you look at those points, they are not in a straight line. So you want to get out a straight edge, and you want to kind of estimate and do the best you can. And when I did it, this is what I came up with. We may or may not have the same example. So you notice it kind of looks like 3 of those points are on the line, and there's 2 on the lower side, there's 1 on the upper side. They kind of look the same distance from the line. That looks pretty good to me. So there's kind of our line. We're just estimating. And Now that we have that line, we want to write an equation of the line, and you know how to do so. You know how to write the line in y equals mx plus b form. All we need to do is find the slope and the intercept. Well, the easiest thing to do is to find the intercept. Remember that? Where it crosses the y-axis. So if I follow that line up there, looks like it's above our scale, but not much. So I'm going to estimate, I'm just going to say it's 17. Again, we're estimating. We're doing the best we can to see what we can do with this line and the data on the graph. Now we want to find the slope, and as you know, finding slope means we can do a couple things. We can use the slope formula, but it's kind of nice. We have 3 points. 3 points. Oh wait, 4 points. 4 points that are on that line. So we can just count between the points. I'm going to start at the top one. If I count down 2 over 1, oh wow, down 2 over 1, down 2 over 1, and I get to another point. And if I keep going, wow, it kind of works. So I was just able to count it on this one and go down 2 over 1. So my slope is -2. Pretty straightforward on that one. It's not always going to be that easy. Using the slope formula, y2 minus y1 over x2 minus x1 is going to probably be a way or a method that you use frequently when our scale's not so easy. Part C says interpret the slope and the y-intercept of the line of fit. So I'm going to start with the slope being -2. That means that because we're going down 2 people over 1 minute, the line reduces by 2 people every minute. Nice. And then we have the intercept. The intercept is at 17, which means 17 people in line. And what did it say? At noon. All right. Predicting the number of people, predicting the number of customers, people in line 8 minutes after noon. So we just come to our timeline and we go to 8 and we go up to where it hits the graph, and then we go over and we see that it's 1 person. So the bank pretty much goes through people fairly quickly, 2 people a minute. And after starting with 17 people, there's only 1 person left in line after 8 minutes. Pretty straightforward. Let's do another one. It says, the table shows the average and maximum longevity of various animals in captivity, etc., etc., etc. Look at the table over here. Voila. As you can see, I've already plotted the points. So if you would, please go ahead and pause the video and graph in your own points right now. And welcome back, part A. Now that we have all of our points on there, part A says draw a scatter plot, whatever we did. What relationship, if any, exists? So as we can see, we kind of see that this line would kind of go up. It's kind of, as the average increases, the maximum increases. So we have a positive linear. And I feel real horrible because most of our examples have been positive linear. Most of them have been positive linear, and they're not always that way. Our last example was negative linear if we had described that relationship. So just know it's not always positive. B, draw a line of fit for the scatter plot, then write in slope-intercept form the equation of the line of that fit. So here, these are kind of spread out. So when I draw a line on this one, mine looks something like this. And in that one, this one doesn't touch or pass through any of those data points. Not like last time where it went through 4. This one doesn't go through any of the pre-existing data points. But it looks to me like there's roughly an equal number, 4 and 4 on each side. It looks like they're roughly the same distance from the line, give or take a little tiny bit, but on average, pretty much the same. And so I'm going to stick with it. I'm going to stick with it. And now I'm going to write my equation in slope-intercept form in y equals mx plus b. And of course, y equals something x. And I'm going to look at my intercept where it crosses the y-axis. And I'm going to estimate that as roughly 28. I don't know. If you said 27 or 29, I'm probably going to be okay with that because we're estimating. And now we need to find the slope. Now here's where I talked about. We can count if we have points, but we don't have any actual points. So what I'm going to do is I'm going to look. And it's easy to use the intercept. The intercept is 0.28 based on what I said. 0.28. And I'm going to look at my line and see, is there any other perfect point that's not one of the data points? And I can see one right there. I see one right there. I circled it in black, but now I'm going to put it in black. That's not a data point because it's a different color. And that point is 40 and 70. 40, 70 is that point. So now I'm taking my x's and I'm subtracting them, my y's and I'm subtracting them. And 40 minus 0 is 40, and 70 minus 28 is 42. And now when I put my change in y over my change in x, that's 42 over 40, simplifying 21 over 20, which as a decimal is 1.05. That decimal is so negligible that I'm going to just say that I have a slope of 1. I'm just going to say it because we're estimating. So now my equation, my final equation, y equals x plus 28. That's what I'm saying it is. And it says, use that to predict the maximum longevity of the animal after an average longevity of 33 years. Well, I'm going to go to the graph. 33 years, right here, and I'm going to take and draw my line up, and it hits the graph roughly there, and over, and I don't know, my line's a little bit high, but I'm going to estimate 61 or 62. And now if I use my equation, and I go y equals, and it says 33 years plus the 28 we said, we add that together, oh wow, that's 61. That's pretty dang darn good. That's pretty dang darn good if you ask me. Oh, I guess that's why I'm a teacher, huh? All right, so ladies and gentlemen, line of fit. You take and you estimate, you draw a line roughly between the points as best you can, and then using the skills and we've learned before about writing the line, the equation of the line in slope-intercept form, bam, and then using that to estimate and predict future numbers. Ladies and gentlemen, pretty straightforward. I have placed on your paper is the quick write, so go ahead and do that. And then we'll talk about that later. And then I just want to put this out there before you go, before you close this out. I know this might be a little bit longer, but I'm going to say it. The next video is not me. The next video I just took offline. I'm asking you in your notes, go ahead and take the notes from the book, from the top of the page that it says there, because I just don't remember and recall off the top of my head. Sorry about that. But I don't. And it's some other guy just talking briefly about the correlation coefficient. We are not going to spend a lot of time on the correlation coefficient. You kind of are just going to get an idea of what it is. Next year in algebra, when you use the calculator, you're going to be able to calculate it. Correlation coefficient being R. It's how strong our line is, how much our line of fit is, and how the data correlates to each other. It's pretty interesting stuff if you're into math. Otherwise, it's a short video of only about 6 minutes. Ladies and gentlemen, thanks for watching that and taking whatever notes you can. And I will talk to you later. Bye now.